Alright, well, I'm gonna click the Go Live button on YouTube. So everything is being recorded. And I'm gonna turn on the live stream of in OBS. There we go. Alright, so are there questions before we start today's lecture? And please use the 2020-0414 text channel, so this way we focus all the discussion of today's lecture over there. Alright, so we got 8 people, including myself, so far. Yay, 9, 10. I'm sounding like the count in Sesame Street. 11.
Count on count.
Alright, well, people are showing up. That's good. I think the live session is helpful, more helpful than having to watch 1 hour and 20 minutes of lecture continuously. So nobody has any questions. Alright, I'm just gonna wait just a little bit, another 2 minutes or so. Alright. Well, hope you guys got a good break. I spent almost the entire break writing code to generate questions for the exam this week, or the exams this week, because I have to write several programs for CISP 310 and several programs for CISP 440, so that there will be a variations of questions. Let's just say. All right. Okay, so Thomas has a question, and we can. Yeah, so Nick is correct that it doesn't quite say return to the end of this block. All it does is to load the address of 5 bytes after the beginning of the LDI opcode into a register. That's basically all it does. All right. Okay. All right. Well, it's officially 5:30. So I'm going to start today's lecture. So I did a whole bunch of programming over spring break. The first kind of programming that I did was to improve the efficiency of the assembler and also the trace analyzer, which is what we'll be using today for at least a certain part of it. So in order to ask one of the questions of what is the dot 5 plus, let me just go ahead and illustrate it using the assembler, okay, because this is a good time to test drive the new assembler, which I have done some already, but it's always good to kind of use it as much as possible before you guys start to use it in the exam. So we'll go to shared and processor, and then we go to the assembler. So you can see there are two assemblers with postfix expressions now. One is RC1, which stands for Release Candidate 1, which basically means, I think it's ready to be used, but it's not officially released yet. So I'm gonna use it today, so that if there is any type of problems, I can spot it. The more I use it, the better I can debug it. Okay, there we go. The assembler is not actually much faster compared to the compared to before, but I did include a few more things in terms of error checking, and also tab does not should not bother um, the assembler as much anymore. Um, I cannot say that it does not bother at all completely, because I haven't tested that, but I think it should not. Okay, so let's go ahead and just write a sub write a program, as a subroutine example. So we usually start with a no op instruction. If you want to use the trace analyzer, you have to make sure that your first instruction starts with a no op. So for the test tomorrow, okay, if there's any type of program you want to run through the trace analyzer, which you are allowed to, just make sure that the first opcode is a no op. Because conventionally we put main at the end, after the subroutines in the C programs, I'm just going to branch around the subroutine. So in this case, I'm going to have a subroutine that does not return anything. So it's a void function. How does the exam work? Okay. So the way the exam is going to work is it is not paper-based anymore. Instead, what I would have you guys to do is so I'm going to describe the whole process tomorrow, which is a day before your exam too. So this way you guys will be better prepared and know exactly what to expect. So basically what you do is you will have a folder for the exam. So all the work, all the programs, all the code, all the answers would go into that folder, and you would basically share that folder with me, or I can set up a whole bunch of folders on my side and then share the folders with each one of you. And then all the work that you do, all the program code, everything, you can even pre-share spreadsheets into that folder. And when I grade, you will just have to name your documents according to the question number, and then that's how I'm going to get your answers. Um, so that's the general idea of how I will be collecting answers for the exam, which also makes timing quite easy to do, because I can just look at the last modification time of a document, and if it is after 7 p.m. on Thursday, I'm gonna give you guys 10 more minutes on Thursday, just because the format has changed. It's Thursday. I might have misspoke. I might have misspoken to say tomorrow, but it means the next lesson. Yep, it starts at 5:30 p.m. Pacific Daylight Saving Time. Just in case someone. Okay, all right. All right, so what I'll do is I'm continuing with my sample program here. So this subroutine doesn't do a single thing. All it does is to say, give me the return address, which is what the stack pointer should be pointing at this point. And then we have to increment the stack pointer to deallocate that byte, and then do a JMPB back to the caller, which is going to be main. So this code you have seen already. This is a really, really basic code that we talked about from the beginning. So here is main. In main, technically speaking, we should do this, to initialize the stack pointer. But in reality, the stack pointer or all the registers are pre-initialized with 0. So technically speaking, you don't have to do it. but it is good to kind of have a line of code to say that, okay, this is how we make sure that the stack pointer is properly initialized. Um, and then what we do, this is how we call the subroutine. Okay, so calling f involves the following code. The first thing we do is to decrement the stack pointer. Well, okay, you can interchange between the order of these two instructions. They don't have to happen in this particular order, but if you exchange the order, then what you put into register A, will have to change. Okay, and then we then push this on the stack, which means we store that to where it's register D the stack point is pointing to. And then we can do a JMPI instruction to the subroutine, which is F. And when it returns, this main has nothing else to do. So when it returns, the stack pointer is already balanced, so to speak, because the subroutine is responsible to deallocate the byte pushed by the caller. So at this point, we can do a halt instruction, and the stack pointer should be back to 0. Okay, so the question that let's see, that Thomas was asking was, what is this dot 5 plus? What does it exactly do? So with this dot 5 plus, first of all, it is a postfix notation, which means we specify the values and then we specify the operation. So in this case, 5 is a value and we know what 5 means. But this dot is representing the address of this particular instruction, of the LDI instruction. So if you have a JMPI instruction, the dot would be representing the address of the JMPI instruction. But because this is a LDI instruction, so the dot is representing the address of the LDI instruction. So whatever the address of the LDI instruction is, the constant that is being loaded into register A at runtime is really just 5 plus the address of LDI. So let's check whether that is the case or not. I don't even need to run the program to know whether that is true or not, because I can look at the assembler or the assemble tab. So here's the assemble tab. The assemble tab has seen a lot of changes in terms of the formulae in the spreadsheet, but from the external point of view, nothing should have been changed. We can talk a little bit about the flags. Sure. Okay, so go ahead and queue up the question. You don't want to type it right now, because otherwise I can kind of lose track. But you want to kind of queue it up using Notepad on your side, so that when I'm done with this, I can move on to that topic. So at this point, we can look up row 13, which is the row that we have questions about. So this 09 of column W is telling us that the LDI instruction is starting at location 09, or the first byte of that instruction is at location 09. And the constant that we are loading into register A is 0E. So now the question is, what is 0E and what is 09? What is the difference between those two in hexadecimal? 0E minus 09 is 04 in hexadecimal, because, well, let me see. It's 05, sorry. It's 05 in hexadecimal. And that's where the 5 is coming in, because it is basically the dot is the 09, which is the beginning address of the LDI instruction, 5 and then plus, so that means we're just adding 5 to 09, which is 0E, and 0E is the first opcode after the JMPI instruction, which is the correct return address, because when the subroutine F is done, we want to continue execution over here. So does that answer Thomas's question? I'm guessing it does. Okay. All right. Okay, so next we're going to move on to Eugene's question. Go ahead, Eugene. You're welcome. So I'm waiting for Eugene to type or use the voice channel to let me know of the question regarding the flags. well, Spencer's typing something. Okay. Oh, okay. That can be problematic because now I have no way to know what question he was about to ask. Okay, well, I can always come back and answer the question when he comes back online. Um, any additional questions, that you guys want me to address before we move on to a slightly newer topic today? Okay. All right. So I'm just gonna type here and ping him. Oh, okay. He stopped me typing. Okay. So to answer this question, I'm going to have you guys to do an exercise to answer that question. So the question is, what is a JXI instruction going to do? Okay. So I'm gonna answer I will not answer the question directly because everything that is needed to answer the question is already in all the resources that you have at this point. Okay. So it's basically a question of how do we analyze and how do we interpret the resources that are currently already available to us to answer that question. Because by being able to do this, you are improving your understanding of the processor, and not just this processor but also in general, how processors work internally. Okay, so let me remove this code over here, and all I'm going to do is to write a really simple instruction, which is a JCI instruction. Okay, so here's JCI, and I don't even bother to use a label, as where it has to go to. I'm just going to pick some random location of 12. Okay, and it's okay to do this too. Okay, all this is really saying is go to location 12 if and only if the carry flag is set, or if the carry flag is a 1. Otherwise, continue with whatever is right after the JCI instruction. So that's how I would describe it in English. Okay, but exactly what does it do? Okay, so this is the part of stuff that I would like all of you to know already by now. Is okay. So first of all, what byte do we or what bytes do we put into the processor to represent this instruction? So the first thing you need to utilize in this case is the opcode table. So you pop onto the opcode table, and then you look up JCI, which is over here. So now you know the JCI opcode is 01000100, which is a 4 in hexadecimal. Okay, but it needs 2 bytes because according to the description of what it actually does is if the carry flag is a 1 or if it is non-zero, then it would dereference the program counter and then use whatever the program counter is pointing to and put it back into the program counter. If the carry flag is not 1, which means it has to be 0 because C is only a single bit, that means the program counter is going to get just program counter plus 1. So the way it works, I think I actually explained how conditional branch instructions work in class already, and I believe that was done before the COVID-19 thing. So you might want to go back to that lecture and kind of go through the whole exercise, because you can run all of this through um, uh, Logisim and look at how the multiplexers and demultiplexers and what register gets enabled in order to understand exactly how the opcode is implemented. So Eugene is still typing, so I'm just gonna go through here. So the only differences between the JLI, JOI, JSI, JCI, and the JZI has to do with what flag they look at in order to decide which branch of the ternary expression to use. So that's the only difference between these 5 instructions. They're all conditional branch instructions based on a single flag in the flags register. So let me bring up the um, Logisim. Okay, so that way we can take a look at the processor. Okay, so Eugene is following up his question, and which one of them is represents in Boolean logic? Okay, so they are not Boolean logic per se. The flags are just flags. I mean, that's all they are. So technically speaking, okay, if you look at the actual implementation, the flags are all determined inside the ALU. So in the ALU, we got the flags. This is the S flag or the sign flag. This is the Z flag. This is the O flag. This is the C flag. And I think that should be all of them. Right. And then there's also the carry flag, I think. So we got the carry flag over here. We got the sign flag over here. We got the zero flag over here. Overflow flag over here. And the carry flag is actually a combination between the carry and the borrow flag, depending on which operation was done. So that all of those flags, okay, the 4 flags go into here. This is basically our L flag because it is the exclusive OR between the sign and the overflow flag, and that's basically what the flags are. Okay, that's it. Um, so by looking or by reading the ALU design, we know exactly how the flags are going to be influenced by various instructions. And how we then utilize the flags to make conditional branches, like if x is less than y, that depends on whether x and y are signed or unsigned. And if it's an equal to, then we are not going to look at the same kind of flag. So that part is that's basically how we compile a program from C to assembly. So I'm not sure whether I answered Eugene's question or not. And if I did not quite answer Eugene's question, I can get a clarification of what specifically. Okay. Yes. So the scope of the second exam covers everything from the microcode of the processor all the way to the implementation of subroutines, calling, returning, passing parameters, returning values, and all of that. So yes, so the scope does include the conversion of Boolean logic from C into assembly and vice versa. The vice versa part has to do with disassembling a program. So you're looking at the assembly code and then you're converting it back into the C code. All right, so looks like there are no additional questions. Alright, so we got a question, talk more on what steps do we need to follow when converting C code from assembly code. Okay, so one thing we can do is to look at some of the assembly code that we have written in the past and then analyze that and then convert it back into C code to our best ability. So that means control structures, the converted C code has to be a structured program without using gotos, and also it has to make use of high level concepts like while, if then else, and then the parameters if possible. We need to know the types of the parameters, like is it a pointer, is it an integer, if it's an integer is it signed, is it unsigned. Sometimes we cannot tell because if the whole program does not have a single JLI versus a JCI, we probably cannot tell the signedness of integers. But if there are JCI and JLI instructions, then the type or the signedness of the integer can be implied. Okay, so I'm not sure whether that question is answered or not. Okay, go over question number 2 in the practice exam that I reviewed last time. Okay, and why do we want to do that? I mean, you want me to go over it again because. Okay, so the question is determining whether a certain bit is important or not. Okay, so I don't have to go back to the question to answer this question. Um, so for instance, let's look at the program counter, which is a register. Okay, so let's look at this register, and okay, so the question is if we know that the program counter is not enabled, okay, then why do I care about what input is what is presented to the D port? We should not, right? Because if the register is not enabled, on the rising edge of the clock is not going to get updated. If it is not going to get updated, who cares what is going into the D port of the register? So if we don't care about what is going into the D port of the register, that means PCMux is irrelevant because I don't really need to know whether PCMux is a 0 or 1 because either way the register is not going to get updated. Or we can look at the RAM component, okay, which is all the way to the right hand side. So with the RAM component, if RAM cell is a 0, then why do I care whether RAM load is specifying a read or write operation? Because it's not either way it doesn't affect the component. The component is not paying attention at all. That is what I mean when I say, if a certain component is not selected or it is not active, then we don't need to know certain parts of what we feed into some of the pins of that particular component. So am I answering Kevin's question? All right. Any other questions before we move on? Okay, regarding question number 2, IREN. So um, IREN is referring to instruction register enable, and I think where is it located? So it doesn't have a name because I did not put a name over here. There's no tunnel corresponding to IREN. So this wire is IREN basically. And then Richard has a question. Do we have an example of where you specifically fill the chart? I was hoping to see whether I'm doing the problem correctly. I want to check the answer. Did I fill in the chart last time? I'm pretty sure I went over the chart and went over each field to indicate which one should be what. Okay. Okay. Um, I do not remember whether I have one already filled in. I'm just gonna take a quick look here. Does not look like that is the case. Um, but I did describe the answers last time. So basically, you can follow my description and then use my description to fill in the blanks. Does that make sense? All right. So let me see if I have the right question here. Yep. All right. So I'm still only going to I mm, I suppose I can fill this in using a different program. Um, all right. So this works better. There we go. There we go. All right. So I cannot use my tablet when I'm using my bigger screen, so I'm just going to use text to fill it in here. All right, so in this question, we're gonna have we would use two microcode to implement this one. Okay, this is what we talked about already. So I'm not gonna spend too much time on why these are the numbers, but we'll just go ahead and just say that's basically what it is. Okay, so PCEN is a 0. Okay. Okay. The problem with this is it does not put the text where I think it should go to. Okay. So I have to put the cursor slightly above a line to get it to get there. And I can probably use a smaller font too. Tools, text font, and we'll go ahead and use a smaller one. There we go. Alright, okay. So if PCN is a 0, then PCMux is just going to be a don't care because it's not going to get updated. Address mux needs to be predetermined because it has to be a specific value because we want one of the registers to drive the address port of RAM. So that means, okay, I'm just visually tracking which one is which one. So it's going to be this one. So that means address mux needs to be a 0. So when we go back to here, address mux needs to be a 0 in this case. I can actually move it after the fact, but it's a pain to use this tool when I'm not using my tablet. Nope. There's a There's a tool to drag a component and move it around. There we go. And of course, it doesn't quite do what I want. Ah, okay. So I'm just gonna point and say something. Okay. So so Richard, you're gonna have to convert what I say to a visual form that you can then interpret and understand. Okay. So ALUOP, okay, is the ALU operation. Now we are just dereferencing, which means the entire ALU is not going to be used. So if the entire ALU is not going to be used, then it doesn't matter what we put into ALUOP, which specifies the operation. So so ALUOP is going to be a zero. Yeah, excuse me. ALUOP is going to be an asterisk. ALUEN is going to be a zero because the ALU is going to be disabled. Um, RO1 demux, okay, which is RO1 demux, is this Y over here. So this one needs we need a specific value because we want to route this wire onto this Y over here. So that means RO1DMX needs to be a 0. Okay. RO1SEL is selecting which register is going out of register output 1 of the register bank. And in this case, we want that to drive the address bus. So it's going to have to specify register C. So that means RO1SEL needs to be a 2 because the number 2 or 10 in binary specifies register C. And then over here we have RO0 demux. So let's go check out where that is going to. So RO1 demux is over here, and it is specifying where register output 0 should go to. So that really needs to go to the data port of RAM, and that the data port of RAM is this wire over here. So that means RO0DMX needs to specify a 2 because we need to connect the input to output 2. So switching back to the table, okay, table. So switching back to the table, this number here needs to be a 2, and then the register we need to we need to select is register A, which is 00 over here. And I misspoke a little bit earlier because we are actually reading from RAM. It doesn't really change, RO0 demux, but I misspoke a little bit earlier. RO0EN needs to be a 1 because we are using register output 0, so it needs to be enabled. RI Okay, I take it back. I take that back. Okay, I am totally wrong in this case. Okay, so register output 1 is not going to be used because we are updating a register. So that means RO0EN, this Y over here, it is going to be a 0. We don't want it to drive anything, which means RO0DMX can be anything. So going back to the table, this is an asterisk. This one here is a 0. This okay, take it back. This one here is an asterisk. This one here is an asterisk. This one here is a 0 because we are not using register output 0 from the register bank. So it doesn't matter what we select, and it also does not matter where we send it to because the demultiplexer needs to be turned off. Register input select needs to specify register A because we are updating register A. So RISEL needs to be a 0. RIEN needs to be a 1 because we are enabling the register input feature. RI mux, register input multiplexer. Okay, let me show you where it is. So that is this one over here. So this one switches what do we use to update the input register? And we need to update it using the data port. So it needs to use input 0 of the two inputs of the multiplexer. So that means in the table, RI mux needs to be a 0. RAM load needs to be a 1 because we are reading from RAM. Our RAM select needs to be a 1 because we do want to enable and read from RAM. And then IREN needs to be a 0 because we are not updating the instruction register. Okay, there we go. So is that okay? All right. Okay, if we could enter the value of the opcode, would we be able to see the status of these elements? Okay, so I know what I'm going to say sounds a little bit pointy, but that was not the intention. Uh, so I'm going to say it now. Why don't you give it a try? So we talked about how to give this a try already. Okay, so let's just look at the instruction that we talked about a little bit earlier, which is 44 for JCI. So the way we hard code that into the processor is not even to hard code it into the instruction register, because we can hard code it into the microcode pointer. So you just type 440, and this is the location 440 in ROM, which corresponds to the first microcode of the opcode 44. So now you can go to different places of the processor, and you can see how PC mux is now a 000 because we're looking at register. I mean, we're looking at the carry flag. PCEN is a 1 because we are about to update the program counter. So yes, so you can answer some parts of the question this way, but this will not show you things that do not matter. In other words, let's take a look here. Register input enable is a 0. We are not updating any registers inside the register bank. So that means RISEL really should not matter. Okay, it doesn't matter what register we specify with RISEL. But RISEL has to have a value. It is going to be 000 in this case. But in the answer in the table, you cannot use a 000. You cannot use 00 because you have to indicate that it does not matter what value we put into RISEL. So to answer Eugene's question, yes, you can, but it doesn't fully answer that question. All right, so Richard has some additional questions. Would RO1 register output 1 demux and RO1 cell ever not matter? Okay. If an operation does not involve a register output 1 from the register bank, then it would not matter. So now the question is, what instructions do not utilize register output 1 from the register bank? I'm not going to answer that question because you can think of it. You can think about which instruction does not make use of the register bank at all. Okay, so Eugene's question or comment is, so we should pay attention to only ones and after that deduct all others. Not necessarily just the ones. It is the ones going into the enable or the ones going into RAM cell, stuff like that. So it's not really just the ones. It is what the one is doing that is important. The bottom line is you have to understand how the processor works, how each component operates, and how they operate as a whole. That is what I need you guys to understand, and that's what the test is going to test, is going to assess. By manually inputting in certain opcodes, we can see the slice of that code. Then we can determine what is 0 and 1. No, you cannot determine what does not matter. You can only see what is a 0 and what is a 1, but what does not matter, because if you look at these wires, okay, I'll give you an example. Okay, if you look at these wires, and you look at RO, okay, I can't click on this wire, but if you can, it's not going to be an asterisk. It's not going to be a not care. It's going to be 0, 0. Okay, but in this case, that 0, 0, 0, 0 should be an asterisk in the table because it really does not matter. So the answer is no. Using this technique can partially help you answer the question, but it cannot help you answer the question entirely because this the simulator does not understand which signal does not matter for a particular operation. Only you can figure that out. Okay, so let's see. We can see this. For example, for the example question, there are two slices. Yes. The second slice is incrementing C, which is what we talked about before the break. So in order to increment register C, you have to figure out what component is needed, what components are not needed, or they do not get updated. So that is what I'm testing. Do you understand how the processor works? Do you understand how the components work together? Is my voice losing? No, no, it's still good here. Is live stream still good? Looks like it's still good. Yep. All right. So any other questions? All right. So apparently there are no additional questions. Okay. I just want to kind of reiterate, what people can do to prepare for this test. Um, it really is boils down to, for certain types of questions, it really boils down to, do we understand what each component is doing? Okay, what is RISEL doing? Okay, well, you look at this component, it's not a standard component in Logisim. So you have to right click on this and go into a register bank and then find out, oh, okay, what does that connect to? And then inside here, what is that wire going to do? What is this wire doing? What is this wire doing? What is this wire doing? Okay, so it is all about um, understanding the components, how they work. But since the test is online and you can use anything, you can use any resource, um, the only exclusion would be anything that involves live communication during the test. So that means Logisim is available to you, and you can utilize Logisim in order to track down the wire connectivity. Like, okay, this is a big huge mess here, but I just need to find out where this wire is connected to. Click on it. Okay, it will turn into bold, and you can quite easily figure out where that wire is going to. So that is one way to help you to answer the question, is to use the tool so that you can quickly locate how components are connected. If you ever forget, okay, how a register works, okay, you can go to help. You can go to help, go to library reference, and then go to memory library, go to register, and there we go. We have the full explanation of what a register is, what each port of a register is doing. So now, do we want to rely on the help and Logisim to figure out things during the test? Hopefully not, right? Because this takes time. So studying means you have to fully understand all of these components by themselves, okay, and also for the most part how they interact with each other before the test, so that you are already familiar with all of that stuff before the test even starts. So how do we study for that? Okay, so how we study for that is going to the opcode table. Okay, so let me go to the opcode table over here. Um, Pick out representative instructions. Okay, for instance, I want to know how the ST instruction works. Okay, so some of these are not implemented. Okay, let me just kind of emphasize which ones are still not implemented. Okay, so the STF is not implemented, and if it has a L df if that is not implemented either. So I think that's all that is not implemented. Okay, so when I said a family of instructions, I basically mean if you look at these instructions, JL, JO, JS, these are without the I. Now, how do they work? How come these are different? How come they have an XX, in the opcode description? And exactly how do they work? How do they work differently compared to the LDI and the JSI? Well, to answer those questions, the best way to do it is to hand assemble a byte using the pattern over here, plant it into Logisim, and then figure out, oh, okay, so the output from the ROM is turning this component on, that thing is about to update, this is how we connect this thing over to that thing, and so on. That is what I want you guys to do to understand how the processor works. It's really just to go into Logisim and step by step track down how they work. Now, if you say, but I really need to run the program to fully understand how it works, then go ahead and use Logisim. Hand assemble or use the assembler to assemble a program, okay, and then put that into the RAM of Logisim, and then use Control T to single clock through the instructions so that you can see clock by clock what the processor is doing with that opcode. Okay, so that should have been done a long time ago. If it has not been done yet, okay, we still got like a little bit less than 2 days to do it. All right. So, are there any additional questions before we move on to a new topic, which is closely related to the stuff that you will encounter in the test? No questions? All right. So, if there are no questions, I'm going to move on to a new topic, but it's still related to stuff that we have already talked about. In other words, it's building upon things that we have already learned. So this is what we're going to learn now. Okay, is basically what is a struct, okay, and how do we deal with structs in assembly language. Okay, so I'm just going to make a example here. Okay, so we have uint8 underscore t. We'll call this x. And then let's say we have an array over here. Okay, an array or a char is basically an 8-bit signed integer. So we can now have a string and we'll allow ourselves up to 4 characters in this string. Upload a copy of the test. Um, oh, I haven't done that. Okay, let me do it now. Let's see. I'm Okay, I'm kind of okay. Let me see if I have already uploaded it to the shared drive. I might have done that. If not, I'll do that. That's a better place to put it. And it's under oldx2, oldexam2, and it's not here. Okay, well, we'll go ahead and upload it here. Um, Alright, so now you can find it inside the share folder under oldexam2 or oldx2 in that folder. Okay. Alright, so getting back to structures. Okay. So let's say we have a definition of a structure like this. Um, let me just ask, does everybody have some exposure to structures from CISP 360? Okay, so we all good? Okay, all right, cool. All right. So we understand what this is, right? Struct X is the name of basically a template. And inside the template, there are two components. The first component has a name of X, and the type is an 8-bit unsigned integer. The second component is a string, which basically is just an array of 4 characters. So in C code, okay, so I'm going to write some C code over here. Okay, and we'll go ahead and say we'll have a local variable. Let's call that var1. Okay, so so here's a variable of the type struct x, and it's var1. And once we have variable 1 as a struct x, now we can say let's turn the x component into let's say 45, and then we'll initialize the string. Okay, we can initialize the string character by character, but let's just say we want it to be a null string at this point. So we want to say, okay, the first byte of the string is going to be a 0, which is the null character, and that's all we're going to do. Okay, we are not even going to bother to make use of variable 1. We just declare, allocate, initialize, and then we go like, forget it, we are not going to do anything with the variable. But this program will still help to illustrate what we need to do in order to turn this into assembly code. All right, so so let me ask you a few questions, okay? Because before we change anything, we need to know where that thing is, okay? So I want you guys to think about, where do you think is variable 1 and member x of variable 1? Where is that? And the second question is, where do you think is var1 dot str? Okay? And then another question, before we even think about the address of each member inside the structure, I want you to think about, where is the structure itself? Okay, where is variable 1 itself? Okay, so we want to compare these addresses. Okay, in other words, we want to look at this, and then we want to ask, how does the address of the entire structure relate to the address of the first member of the structure? And how does the address of the first member of the structure relate to the address of the second member of the structure? Those are the questions that we want to kind of think about first before we proceed any further. So I got somebody typing, but I'm not seeing anything in the text channel. All right, so where do you think is var1? In other words, this is a local variable, and since I did not specify static, it is an auto local variable. So where in memory is it located? All right, it is indeed the stack. Okay, so very good. But the next question is, how many bytes should variable 1 take up on the stack? Okay, so that's the next question. So to answer that question, no, it is not 1 byte, because it is a structure after all. And how many bytes do we need for this structure? We need 5 bytes. Very good. Okay, so x takes up 1 byte because it is just a 1 byte 8-bit, or it's an 8-bit unsigned integer, and the string takes up 4 bytes. So the minimum it's going to take up is 5 bytes. Now, does that mean, when you put this program into GCC and you compile it, and then you ask how big is a struct x, it's going to say 5? The answer is no. Okay, so when GCC compiles this program, it's going to say struct x is significantly bigger than 5 bytes. Okay, but that has to do with optimization of how we use memory in a 64-bit architecture and a few other things. And since the toy processor is only an 8-bit processor, we pack everything. Okay, we basically use as little RAM as possible when it comes to stuff like this. Okay, so the address of the structure is in fact the address of the first member of the structure. Very good, Ramsey. That is exactly true. Okay, So when you look at these two, they are indeed the same. Okay, there's an equality here. Okay, now in C and C++, because it's a strongly typed programming language, this equal equal will never compile because the type of the left hand side is a pointer to a struct x, but the pointer type of the right hand side is a pointer to a uint8 underscore t. So in C and C++, it will never let you do it. Okay, but you can always cast these things first. So if you cast each one into a void pointer first, then you can actually compare, and that comparison will return true because they indeed are the same. So now the question is, now that we know where the first member of the structure is located, where do you think the second one is located? The second byte. Very good. Okay, onward. Exactly. So it's going to take up the second, third, fourth, and fifth byte of a struct X. Okay, very good. Okay, so that seems to make sense, right? So now if we want to answer the question and say, okay, let's put this into the context of the toy processor, okay? We know the stack pointer starts at location 0, 0 because that's where we want it to point to when there's nothing on the stack. So where do you think var1 is going to be located if we initialize this properly? We know that it's going to take up 5 bytes, right? So it's going to be 0, 0 minus 5, right? So 0, 0, which is also the same thing as 256 or 100 in hexadecimal. When you subtract 5 from that, what do we get? In other words, if I want to calculate 0x100 minus 5, what is the answer to that question? Can we do subtraction in hexadecimal? Come on, you guys can do it. A 0 is essentially the same thing as a 16. So 16 minus 5 is, we get 100 because that 1 is implicit. So we can do the same thing with 0, 0 minus 0, 5. Okay, it will give us the same answer. So what is that? All right, so let's do this. FB, very good. Okay, so FB is the correct answer. So let's just focus on this, okay? And we're gonna write some program here, and just so that we can distinguish the program working versus not working, we'll just make this lowercase a, which is 65 in decimal, okay? Because everything is pre-initialized with 0, so it's no fun, okay? Yep, FB is the same thing as representing -5, but in this case, because it's an address, so we don't look at it as -5, even though it has the same bit pattern as -5. Okay. All right. So let's go ahead and write the assembly code corresponding to this C code, and I'm going to use a new window for that. Okay. So the first thing we need to do, and I need to be mindful because I can resize the window so this way I can see where the edge is visually. There we go. All right. So the first thing is, how do we define the structure in assembly? Well, the answer is you cannot, and yet you can. So the cannot refers to syntax. There's no syntax in assembly language, and not just my toy processor, but any assembler out there that can actually understand what a structure is. But what we can do, okay, is to have a systematic way to use our labels in order to define offsets to members from the beginning of a structure. Okay, so we'll start with x, which is the name of the structure itself, and underscore, and then the name of the member inside the structure. In this case, is a lowercase x. Okay, and yeah, that looks kind of funny, but that's the way it is. Okay, the uppercase x is referring to the structure name, and the lowercase x is referring to the member in this case. So this is going to be 0. Okay. In other words, member X is at the beginning of a struct X. Is that okay? So the address of the first member is at the beginning of the entire structure itself, and therefore the offset from the beginning of a structure to member X lowercase x is going to be 0. So are we good with this definition of what the symbol is representing? X underscore X. All right, no questions, so I'm going to move on. Okay. So the next thing we want to define is, where do we find str? Now we are very tempted to say just 1, right? That seems good because it is 1, okay? But I'm not going to express it as 1, okay? Because I lower the notepad. You mean like this? Okay. But I don't want to express it like this. Exactly. I want to express this as x plus 1, x1 plus, okay? So it's going to be x underscore x1 plus, because I want it to be relative to the member that is right before it. Okay, so this x underscore x here is the offset to get to the previous member, and then this one is the size of the previous member, and then this plus is just doing, saying, oh, okay, just add the size of the previous member to the offset to the previous member. Now we get to the offset to the second member. Okay. And then, okay, this may sound kind of weird, but I need another label to say what is the size of a struct X. Okay, so the size of that thing is x underscore str, which is the offset to the last member of this structure, and then we also have to add the size of that thing. Okay, so I know I used the 4 over here, which is a bad idea. So we'll just say string length over here. We'll call it buffer length. Okay. And then in C, you can use pound define, or you can use a const to define this sort of stuff. So we'll say this is just 4 over here. And then in assembly code, we do not have pound define, but we can always say buffer length is just defined to be 4. So now we can refer to that 4 over here and say buffer length and then plus. There we go. So are we still doing okay so far with the assembly code? We are only defining the labels so that if we know where a structure is, now we know how to access the individual members of that structure. And we also know how big a structure is. Not always. Okay, so to answer the question of do we always need a size label, it's not always, but most of the time we do, because when you allocate that structure, you need to know how much to decrement from the stack pointer to allocate for that structure. So it's almost always necessary, even though it's not like always. Yep. Okay. So we can just test out this piece of code, okay? Even though it doesn't do a single thing, it doesn't emit a single opcode in this case, it's still useful to find out, okay, does it assemble? And if it does assemble, what happened to all those label definitions, So we want to understand all of this stuff here, before we even write the first line of code. So I'm just going to copy and paste over here. And the assembler is getting his job done, okay? And when you go to the Assemble tab, you'll see nothing. Okay, not quite nothing, but nothing really of any value over here. Everything is 0. Look at column V. Everything is a 0 over here, because the entire program up to this point is just defining a bunch of labels. It's kind of like giving you a whole bunch of bookmarks, okay? And you have 4 bookmarks on your hand, and I'm asking you, what is on page 1? What? What are you talking about? I don't even have a book. I just got a whole bunch of bookmarks. That's basically what labels are. They are basically bookmarks. And opcode, which are pages in a book, you need instructions to generate, opcodes. So that is not very interesting, But we can still figure out, what those labels are defined to when we look at the um, uh, sim tab inside the spreadsheet. So you can see that buffer length is defined to be 4. The RPN member is defining basically, how we resolve the value of a particular label. X underscore X is resolving to a constant of 0. X underscore string is resolving to a value of 1. And then X underscore size is resolving to a value of 5. So everything is just kind of as expected, but it's good to have a confirmation that the labels are now properly defined. This thing here, column B of the symbol table, don't mess around with it. It's needed in order for the assembler to work. Okay, so don't change anything in the sim tab of the assembler, but it's useful to read cell A1, just so that you can find out how the labels eventually, how they got defined eventually. Column B is calculating the entire length of the program. So in this case, this program only has 4 lines, and that's why there's a 4 over here. And this is how I can make the columns truly independent of the length of the program. I used to have a hard limit of 300 lines because I only copy and paste the cells up to 300 rows in the spreadsheet. That is no longer the case. It is now truly unlimited. If you have like 1,000 lines of assembly code, it will still be able to handle it. Now, of course, since the RAM only has 256 locations, you will need a lot of comments and label definitions to fill up 1,000 lines, for the processor that we are working with. Time to write Doom. Well, maybe not quite Doom. So if anyone is ever interested in how things are written, you can see how I converted everything to make use of array formula in Google Sheet um, on a smart fridge. I suspect you can run Doom on many devices now. I wonder what game over looks like, when you run Doom on a smart fridge. Would that turn the fridge into an oven? That would be pretty interesting. Game over. Your food is now completely gone. All right, so now let's move on and continue with this program, okay? Because we are only declaring the variables at this point, or defining the labels corresponding to the offset of members. So we'll go ahead and continue and code this whole thing. All right, so now we can specify the no op jmpi to main, okay? And of course, in this particular case, we don't need that, okay, because we don't have any subroutines. But if you just say, okay, I want to do something that is always going to work, okay, fine, it's not a problem. Okay, so now we got the stack pointer initialized. The next question now is, oh, we need to allocate for local variable var1. How are we going to do that? Well, this is how you do it. Okay, so I'm going to write it first, and then I'll explain what it is. So you put x underscore size into a register. So in this case, it can be registers A, B, or C, because none of those registers have any special meaning at this point. So now we do a subtraction. So we subtract all of those from register D. Okay, so that decrement DA is something that you guys have to really watch out for, because the exam, is going to test whether you guys understand the opcodes and the mnemonics or not. Okay, so make sure that, and you can use the assembler to check all of that stuff. I'll show you guys later how to do that. Okay, but for now, let's just focus on what these instructions are doing. Okay, so we are allocating space for local variable var1, okay, because we're decreasing the stack pointer by the number of bytes of the structure. Okay, so now that we have done all the allocation, let's do the usual thing of defining a label to so that we can find a local variable more easily. Okay, so in this case we have var1, which is the name of the variable, and it is now defined to be 0. Okay, because it's the last thing that we allocate for main, so that's why it is 0 byte away from the stack pointer um, in terms of how the labels is defined. Okay, there we go. All right, so now we can move on to line 13 of the assembly code. The 45 is pretty easy. So we are not too concerned about the 45. We are much more concerned about where do we find member X of var1. Okay, and Eugene is typing something. So D in this case holds the D is the stack pointer. D is the stack pointer, and that's its job is to point to the last location that was allocated on the stack. And Ramsey is correct. The stack pointer will now be FB by the time we get to line 14 of the assembly code, which is basically where the variable is. Okay, but we don't want to use we don't want to use the stack pointer to access variable one, because that's an assumption. If we change the program and we say, oh, guess what? We have another local variable here, and it is just an array. Okay, so we have char, and we'll call this local buffer, and we'll allocate 24 bytes over here. Okay, if we made the change like that and you want your assembly code to reflect that, now the stack pointer is no longer pointing to var1. Well, it is still pointing to var1, excuse me. So you have to define this after struct x var1 in order to change that ordering. So you have to do something like this. There we go. So now, because local buff is the last thing to allocate from the stack, so that means var1 is no longer what the stack pointer is directly pointing to, because we have to add 24 to the stack pointer to get to where var1 is located. So it is always good not to make any assumptions to shortcut stuff. Okay, instead of doing this shortcut stuff, okay, we are going to use the label var1. Okay, so now we can, so let's not consider line 12 at this point. We're just going to comment it out. Okay, so we are now focusing on line 15 again. How do we put something into the X member of var1? Okay, the first thing is we need to find the beginning of the structure first. Okay, so to find the beginning of the structure, we have LDI A, and then the label corresponding to the offset to the thing that we want relative to the stack pointer, which is var1. And then we add the stack pointer to that offset. So at this point, A is the address of var1. Okay, so line 15 and line 16 is pretty standardized code to find something on the stack. Okay, so we to get to the address of something that is on the stack, can be a local variable, can be a parameter. So it's nothing new to us. Should not be anything new to us. Okay. So the next question is, but this is not where we want, right? Because we want to get to member X. So at this point, I'm going to break it up into multiple instructions. This is not the optimal way of doing things, but it's a better way in terms of how we explain something. Okay, so we're going to load x underscore x into register B. Okay, so register B is the offset to member X in a struct X. Okay, so now that we know where we can find the variable, which is in register A, and we know the offset to find member X in a struct X. Okay, so we just have to add those two together. Okay, so we say add AB. So now A is the address of member X of var1. Now we know where it is. register B is no longer useful at this point, I can reuse it for the constant on the right hand side of the assignment. And then we can do a store and actually put that into var1.x. So var1.x equals 5 is now finally done. So when you look at this code, you go like, wow, that is a lot of useless code. Because, guess what? var1 is a 0. X underscore x is also a 0. So we are doing a whole bunch of code that could have been done by this. Okay. Yes, register B is only used as a temporary. Well, all the registers are basically temporary except for register D, which is our stack pointer. So we are basically saying, are you saying that this is the preferred way of doing things when two lines could have done exactly the same thing? Yes, that is exactly what I'm saying. I'm preferring lines 15 to 20 to lines 20 to 23 because this code here, okay, from line 15 to line 20, they can stay exactly the same. If you want to define additional local variables after var1, you don't have to change this code over here. If you want to exchange the order of these two members inside the struct x, you don't have to change this code. All you do is to change how we define the labels. So var1 would be changed if you want to define some additional local variables after var1. Yeah, you have to change that label. If you want to exchange the order of x and string, as members inside the struct x, yes, you will have to change these two lines of code and also the third line of code too, because buff length is referring to the size of str. So if you exchange the order, then you should refer to x underscore x and then a 1 plus, instead of string x underscore string and buff length. But those are changes to the labels, okay, which you have to change anyway. But then you don't have to change this kind of code, which can be sprinkled in your entire program all over the place. So the question is, do you want to save some code by making certain assumptions and then have this kind of code sprinkled all around, and then later on when you choose to change the structure of the C program, you have to go back and locate every single one of these instances and change it? Or do you want to do it in a way to use symbolic names so that you don't have to ever go back to change anything anymore? Okay, the answer, to at least to me, is pretty clear. Okay, I would much rather just make the program slightly longer, so that it is flexible and it would be more resistant to changes in the future, or you can adapt to changes in the future. All right, so I'm just explaining why we are doing it like this. So does it mean that we cannot optimize this program anymore? Well, there are certain places we can optimize, because if you look at register A after line 18, it really is just x underscore x plus var1 plus the stack pointer. So what we can do, okay, I'm going to present the code first before I remove the code that is less efficient. So we could have done something like this. Okay, we could have specified x underscore x over here and do a plus. In other words, we are basically we're adding the displacement from the stack pointer to the beginning of the structure, and also the displacement from the beginning of the structure to the member. We can add these two together because these two are both labels, which means the value of these two labels are defined, or they are already fixed at assemble time. So there's no need to waste runtime code to do this addition. Are we referring to line 23? Okay, there are several LDI instructions. Are we referring to line 23? Yep, okay. So basically A just gets var1 plus the label var1, not the actual structure var1, plus the label x plus x, x underscore x. Okay. All right. So then we can add AD just once, and we are done. Okay, at this point, A is the address of member X inside var1. So at this point, A is the address of var1.x. So now we can just do the second part, which is LDI B45 and then ST to where A points to, and then register B over here. So is that okay? Does everybody understand how I optimized line 15 to 18 to just two lines, which is lines 23 to line 24, without losing the flexibility of I can not dynamically, but later on I can change the structure and also change my local variable definitions, and not having to impact how I write line 23. Okay, not really to which part? Oops. Okay, so to answer Eugene's question, I combine four lines into two. And I think we are out of time today, just a little bit out of time. All right, well, okay, so this is how we can do this. Okay, um, so at this point, A equals to var1 the label, right? And we load B with x underscore x. So at this point, okay, I see. Okay, I'm still missing one line of code here. I'm missing add AD over here. Okay, is that the confusion? We still need the add AD instruction. Oh, I have the add AD over here. Okay, never mind. Okay, so I got it earlier. Exactly. So is it Riju? Raiju? Riju? So so Raju got the right idea, okay? Because in the end, all we want, okay, RJ, okay, thank you. So what RJ is correct because in the end, all I really want is A, register A needs to be the value of the stack pointer, but this can only be determined at runtime, plus the label var1, which is determined at assemble time, plus the value of x underscore x, which is also assembled at assemble time. So you can see out of these three things, two can be determined at assemble time. These two can be determined at assemble time. So that means there's no need for me to perform the addition of these two during runtime separately. And that's what I'm doing with the second version of the code, which basically determine the sum of var1 and x underscore x at assemble time so that I don't need to waste another add instruction at runtime. So is that okay? So if you want to change the size of any of the struct member, you have to change the constants. That is correct. Okay, so I know we are running out of time, but I do want to illustrate, how to do this, and then we'll go ahead and terminate or stop tonight's lecture. So if I want to say, x, y, and a z, okay, so we have, two additional single byte members, okay, then we can go back here and say, okay, we can string is no longer where we think it is supposed to be at because now we have x underscore y, which is x underscore x 1 plus, and then we also have x underscore z, which is x underscore y 1 plus, and then x string is going to be relative to the the thing that was defined right before, which is z this time, and that's all I need to do. Okay, oops, I had a typo over here, but this is all I have to do. After this, the size of a struct x is automatically updated correctly. I don't have to change any code down here anymore. So is that answering RJ's point? Okay, I hope so. Okay, yes. Okay, very good. So one last thing, absolutely last thing before I end today's lecture is why do we bother with this? Okay, because who cares where we find each member in the structure, and who wants to convert C code into assembly code and make sure that the assembly code has exactly the same representation when it comes to structures as the original C code? Why do we want to work with this kind of code? That is not a bad question, okay? Because we don't want to learn anything that is actually useless when we get to work. So to answer that question, and this part is optional. If you want to sign off at this point, that's fine with me. So, but I do want to point out why that is important. Uh-oh, this is not good. Um, okay, because I just lost my index page. I wonder how that happens. Okay, let me. I really want to show you what the rationale behind all of this. So just give me a moment here. I just have to find the path without doing this, without using the links. Uh, okay, I have index.html. Okay, let's try that. Okay, that's the index.html. There we go. Okay, so I want to go to develops and then go to the real-time kernel. So as I said, if you want to sign off, it's okay. But if you want to understand why this topic is important, I just have some additional stuff over here. I can't seem to find the sample test we went over. It's not on Canvas. It is in the shared folder under old x1, old x2, excuse me, old exam 2. Or did we go over a different one the Thursday before break? Okay, all right, cool. Thank you, Anthony. All right, so getting back to why the topic of today, and probably will continue this topic next week as well. Why is it important? So this is my real-time kernel, okay, that I wrote, and it's not a toy real-time kernel. This is actually a real-time kernel that I used with some of my projects. Um, so when you look at the API, okay, so I want to show you the quote-unquote API. So the API is down here in section 6, and I'll show you one of these things. Okay, so let me show you. Okay, I can show you this part first. Okay, struct q. Okay, struct q is a type that defines objects, that represents a queue of threads, and then there's also a struct thread, struct tick, and so on. But when you look at the an actual subroutine, it is this is how it's documented. And you look at this and go like, well, it looks like it's just a regular C function. Okay, RTK real-time kernel thread add to add a thread to to be parallel to all the other threads. This is all just basically C syntax, okay, to define the prototype of a function. Okay, so that's all kind of cool. But when you look at the actual code of the real-time kernel, it is all written in assembly. I can show you the code that is all written in assembly after I download it, and I think it's under here, but I need to find it first. There we go. Downloading and installing. Oh no, I lost the file. But okay, so the bottom line is it's the entire real-time kernel is written in assembly. There's no way you can write a real-time kernel, at least not the majority of it, in C code because you need to terminate a function before it gets to the return, and sometimes you have to resume a thread which cannot be specified using C code at all. So the program is all written in assembly, and yet it has an API to interface with C code. That this is the reason why we are doing what we are doing in today's lecture, is so that you can write highly efficient code that is otherwise unspecifiable in C or any high level language. You can write that part in assembly code, but it can work with C code in general. So that really is the reason why we are talking about the topics that we are going over in today's lecture. Um, so I'm going to stop the lecture at this point, because I can keep on and talking about this. For anyone who's interested in this, I can stay online, after the lecture, so you guys can, if you want to ask questions, I can answer those questions. If not, I will go ahead and just stop the recording first,